Okay, welcome back, everybody. We should have a better connection. I'm in my hotel room, so we're hooked up solid now. So my apologies for the last two sessions that didn't go so well. Uh, I'll be back on the road on Tuesday. Tuesday will be, I'll need to find another place to do the final lecture part. But, you know, we really got what one next week is the final. So what I want to do today is finish up chapter 14 and 15, and then possibly 16. We might be done completely, so we'll see how it goes. And then next Tuesday, if we get them all knocked out, it'll be basically a study time. And if you have questions, I'll be here on the road, obviously, but I'll be here and you can come with any questions that you may have, okay? Now, remember, the other aspect is this: if you have any assignments that you have not turned in, everything shuts down with respect to Canvas on the 21st. So make sure you go back and complete. The other aspect, if, for example, for the homeworks, you turned in the original homework on time, and you decide you want to go back and do the second attempt if you did not do the second attempt, and you decide to do it and you got a better score the second time around, what happens, Canvas treats it as the second attempt is a late entry and doesn't give you full credit. So if that happens to you, and I repeat, only if the first attempt was on time, I will go back and obviously correct that and take care of the penalty that Canvas put in there, okay? Also, too, if, again, Canvas doesn't give you credit for an answer that you know is correct, by all means, I'll give you credit. There are some, like, for example, the nomenclature exam, I haven't figured out why, but the answer is correct, but for some reason, Canvas counts it incorrect. I don't know why. I've been trying to figure that out. So I always go back into nomenclature and I look at what you've done, and I do, obviously, you may have noticed, give you credit for some of the answers, which also a reminder is nomenclature. Multiple attempts you can do. It may or may not affect your grade, but whatever the case is, you have to score at least an 80% to get the full credit, okay? All right, so if you score anything less, you know, it sets back to 0. So, and it can have an effect if you're on the border. It can push you up or down, you know, depending where you're at. So, and or if you're in the middle of the scale, it may have no effect at all. All right. So, any questions before I begin? Well, the only thing I can drop, it drops automatically, is the homework. Homeworks are, if you see, I believe three homeworks are dropped, and then it keeps the best. Non-3 attempts. There's 14, 15 chapters, 14 homework assignments. Okay. And then if you did miss an exam, if you recall from the syllabus, I am allowed to take the final grade exam and replace that grade with any missed exam that you did, exams 1 through 5. So that's just a reminder on that aspect. I can do that only, unfortunately, for one. Okay. That is correct with respect to the labs. Let me go back and I'll share with you the assignments here. Bear with me. Okay. So in your homework, you'll see that there is one rule here where in the homework, it will drop the lowest 3 scores. Okay. With respect to the onlines, no, that's not the case. Or any exams. So, any other questions concerning that? All right. Well, let me continue with the chapter. We were talking about intermolecular forces. Okay. And the point, the takeaway from that was that to determine we had 4 intermolecular forces for the molecule that the molecules deal with. Okay, we had London dispersion forces, we had dipole forces, we had hydrogen bridging forces, and ion dipole forces. Okay, these are intermolecular forces. These are forces in where molecules interact with other molecules. Okay, now how we define it or assign what type of force they have was determined by the polarity of the molecule. Now, how we assign the polarity of the molecule was dependent on the type of molecule and whether it had polar bonds or not. Okay, so how it's all tied in, and whether it had polar bonds was determined whether if the molecules, the atoms that were bonded were either the same, which ended up in equal sharing, unless it was carbon-hydrogen bond, which we consider that as a nonpolar bond, or whether the 2 atoms bonded were not the same, and therefore a dipole, permanent dipole was created. Okay, so once we learned that, and then we learned that any compound, any molecule that had all nonpolar bonds would result in being a nonpolar molecule. And any polar molecule, any polar molecule that had obviously polar bonds and those polar bonds did not cancel each other out, was then itself polar. If the polar molecules cancel each other out, okay, then we resulted in a net nonpolar molecule. Once we determine the polarity of the molecule, then we assign it to be, well, if it's all nonpolar molecule, then it would be assigned to London dispersion forces. If there was a polar molecule, we had to then determine, okay, was it a nitrogen, oxygen, or fluoride bonded to hydrogen? If that was the case, then it had a special dipole bond, which was called the hydrogen bridging force, which was the strongest of the 3. If it did not have a hydrogen bonded to a nitrogen, oxygen, or fluoride, then it just was simply a dipole interaction between the molecules, excuse me. And then the last one was an ion dipole, which is a result of an ionic compound, which we all know by now, hopefully, what is considered an ionic compound, and that is the combination of a metal and a non-metal dispersed, whatever extent of dispersion, be it 100% or even a small percentage in an aqueous system. Okay, so once we assign that, then we can do a compare and contrast, because the dipole forces were the weakest, the hydrogen bridging forces were the strongest, and then the dipole interactions were in between. Okay, and so we think of it in terms as if these forces are very strong, they would hold on to each other strongly. And therefore, to break these molecules apart from each other because of the interactions that they have, we needed to add maybe a small amount of energy or a large amount of energy. And that being the case, if we were to do a compare and contrast, if something had something like the weak forces, like dipole forces, and we're comparing it with something that had hydrogen bridging forces, then we know that something with hydrogen bridging forces will require a lot more energy to convert it from gold to you have it go into the vapor phase. So its boiling point would be much greater, okay? And all these interactions or physical properties that we dealt with boiling point, surface tension, vapor pressure, and viscosity. All right, so vapor pressure is the pressure exerted of gas molecules above a liquid in a closed container, okay? And so the strong IMS would have a lower vapor pressure, okay? Lower vapor pressure, because shown by this diagram here, you can see that down here in the bottom is represented by the molecules in the liquid phase. And if these interactions that hold these molecules together, okay, that cause them to attract to each other, remember, because they have a somewhat of a dipole occurring. They've got the partial positive and partial negative section, and they're interacting with each other because of this disparity between a positive and a negative. And if that force was weak, then these molecules could readily go into the vapor phase shown up here with not much energy when compared to, let's say, over here, B, where we see very few molecules in the vapor phase compared to A. And so that infers that molecules of B hold on to each other, attract to each other much stronger than the ones in A, okay? So that would suggest, based on just the analysis of the picture of the diagram, that A, okay, would have the weaker IMF, the weaker intermolecular force. And that results with more gas molecules in the gas phase, which would that result in a higher vapor pressure, okay? Higher vapor pressure, because sometimes, you know, people have a hard time seeing this, and let me demonstrate it in this manner. Let's assume that on this, it's a closed container, and we can put a gauge over here, a pressure gauge inserted in here on both sides, okay? And that vapor gauge will measure the amount of pressure just like your air pressure in your tire. If there's more molecules in the vapor phase, our pressure is going to be greater, okay, on the left side than it is on the right side, okay? All right. Now, with respect to boiling, that is the temperature, okay, that the liquid is converted to the gas phase, okay? And so again, by extrapolation of what we just talked about, you can infer that to break that interaction up, to cause these molecules to break apart from and go from the liquid to the gas phase, if they're being held on very tightly, it's going to take a lot more energy. And so the stronger the IMF would result in having a higher boiling point. Because again, those molecules are being held on to each other. Now, keep in mind, we're not talking about chemical bonds being broken up, okay? Water, when it goes from the liquid to the gas phase, we're not breaking water up. We are breaking the interaction of the water molecules have with each other, okay, to break them apart. Think of it in terms of this interaction as an analogy is two magnets. You know, if you have relatively weak magnets and you put them together, say like refrigerator magnets, you know, it doesn't take much energy and force to pull them apart. But there are some very high powerful magnets, and I worked with some in my field many years ago, that when they snap together, it takes a lot of force to pull them apart, a lot of force. So think of it in terms of that, and maybe in that means. So If the IMF interaction is very strong, those molecules are like the strong magnets, examples I use in there. They're held onto each other very tightly. And for me to separate them, I need to exert a lot of force and energy into there to get them apart, as compared to, refrigerator magnets that are, fairly weak, and I don't require that much force to get them separated, okay? The same is true with the melting point. We use the example of the boiling point, but the melting point is the same thing in the sense that that's where the boiling point is going from a liquid to a gas phase. The melting point is the process of going from a solid to the liquid. And so the same interaction, you've got a solid material, we put energy into the system, we're trying to break up this interaction in the solid phase and then cause the molecules to separate from themselves a little bit better and go into the liquid phase, okay? Much like a stick of butter. You take a stick of butter out of the refrigerator, it's nice, hard and firm, right? But leave it on the tabletop for a few minutes. What does it start to do? It starts to soften up, starts to melt. That is what we call the melting point, the melting. Surface tension, again, what holds the molecules together affects the surface tension. So a stronger IMF, strong intermolecular force, will cause the surface tension to be greater, okay? Much greater. And this would be a diagram to demonstrate that. Whereas A versus B, the fact that A, say, bubbles up a little more, like more of a droplet, that's because the molecules are attracted to each other and they're drawn to each other much greater, much stronger than the example of B, where the liquid kind of spreads out a little bit easier because there's less interaction. I should say less. The strength of the interaction is greater, less than for B than it is for A, okay? Now, viscosity is the resistance of a liquid to flow. And we're all familiar with viscosity. Classic example I've used a few times is honey. We know how thick honey is. And if you had a cup of honey and a cup of water, and you did the race to see who empties that cup quicker, obviously that's gonna happen. The water will be emptied quicker than the honey will, okay? And that's because the molecules in the honey are held on to each other, or holding on to each other much stronger than it is in the case of water. Now, you think about it, how can we make honey flow, or any viscous material flow, a little faster? What do? We heat it up, right? If you want honey to flow a little faster, you heat it up, the molecules get separated a little further, and now it starts to flow a little greater. Yeah. All right, so like in this example, vodka flows rapidly compared to honey, obviously, all right? So the IMF would be higher for honey. All right, so here in this question, you're being asked, comparing ammonia to fluorine, okay? And so we're going to compare, and obviously we're going to compare and say, when we do comparison, point number one about all this, we cannot make absolute values. In other words, we can't say, look at ammonia and tell me the exact boiling point of ammonia. No. What we can do is this. We can take two molecules, and based on their structure, based on their polarity, we can then determine who we would anticipate to have a higher boiling point, a higher vapor pressure, a higher viscosity, or a higher surface tension, okay? Or vice versa, lower, however you ask the question. And we do that by, first, we need the formula of the compound. Once we know the formula, we need to determine its polarity, okay? And once we know its polarity, then we can assign a particular IMF. And once we know that, we can answer the questions. And so to determine the formula, you may need to know, go back and review how you did the Lewis-Dot structure. Okay, because we did a lot of examples of that. And at that time, I told you, remember this, that whenever you get certain properties in the Lewis-Dot structure, you will always have a polar molecule. All right, so ammonia had the following formula, which we did this a few times, but we did the Lewis-Dot structure, and we ended up, nitrogen is obviously the central atom. And so we had 3 hydrogens bonded to each other, bonded to the nitrogen, I should say, and we ended up with 2 lone pairs on the central atom, okay? That right there in itself, the fact that it has 2 lone pairs in the central atom should tell you, okay, I got a polar molecule, okay? I got a polar molecule. Now the question is, which IMF do I assign it, okay? Knowing that it's polar, definitely it's not going to be London dispersion forces. There's no mention, so London dispersion forces can be eliminated, okay? We can also eliminate ion dipole, okay? And why is that? Because there's no mention here of any ion. No, we have no ionic compounds here. We just simply have ammonia. And so what is left is the dipole-dipole or the hydrogen bridging force, right? So now we have to determine, remember hydrogen bridging force dealt with hydrogen bonded to nitrogen, to oxygen, and to fluoride. Guess what? We have this scenario right there. So that automatically tells us that we have the IMF for this example for ammonia is the hydrogen bridging force. So we know the formula. From the formula, we get the polarity of the molecule. From the polarity of the molecule, we determine what force we're dealing with. So ammonia has hydrogen bridging force, which, a mental note, is of the 3, is the highest IMF interaction, okay? So we do that for ammonia. The next thing we do is we look at fluorine, okay? We're dealing with fluorine. So it's simply the diatomic F2, you've written like that or as so. It's a diatomic molecule, okay? There's an equal sharing of that bond. So therefore, well, we can do the Lewis-Dot structure if you like. You can verify this, but you should end up with something like this. Okay. Diatomic molecule. And that tells us that we have a non-polar species, non-polar, which then further tells us that we're dealing with London dispersion forces. That's it. Okay, we don't have to worry about the other ones because it's non-polar. All non-polar molecules, the only force they got to deal with is London dispersion forces. Now, so we've assigned the LDF, or excuse me, the IMF for the molecules. And let's clear this up and let's go with the questions. So we write the formulas. From the formulas, we determine, like we just discussed, what force we're dealing with, okay? So now, with that information, we can start answering some questions with respect to the physical properties. And the first one would be, all right, which would has the stronger IMF? Well, as I stated, HBF, hydrogen bridging force, is the strongest of the 3. Okay, so ammonia would have the stronger IMF. Now you're being asked, which has a lower boiling point? Think this through in your head now. I got a lower boiling point compared to the other molecules, so that would suggest that it must be the molecule that has the weaker IMF. The weaker IMF, which in this case is fluorine, because it has the London force. Okay, which is polar. Well, we went through that scenario earlier, and ammonia is the one that is polar. and then which would have the higher vapor pressure. Keep in mind, not the boiling point, don't get it mixed up. This is a closed container, one with fluorine and one with ammonia, and we're measuring the vapor pressure, okay? And again, that would be the one with the weaker force, which is the London force, which means it's fluorine. Okay? The more molecules would be in the gas phase than those with the higher or the stronger IMF. And then which would be the least viscous? Now, when you look at these questions, make sure you're reading them correctly, because some, this question, all these questions could be reversed. Like number one could say, which has the weaker IMF, right? Number two, which has the higher boiling point? Number five, it could be, which is the most viscous? The question could be asked. Here, the question is, which is the least viscous? And being the least viscous is fluorine, because it has the weaker force. Okay? And then the surface tension. Okay, again, we're asking the question, which has more surface tension? And that would be the one with the stronger IMF, in this case, ammonia. All right, so with this scenario, where we use the example of ammonia and fluorine, but we can do that with any molecule, okay? So the takeaway here is this: if you're given two molecules and you don't know, we'll write down if it's, which is the central atom, if you need to know, in case you need to know that. And then from that, you can write the Lewis dot structure. And from that, you can determine to make sure that if it has polar bonds, if the polar bonds don't cancel out, and if they don't cancel out, then it's a polar molecule. If they do cancel out, then then it's a nonpolar molecule. Okay, if it's diatomic, it's nonpolar automatically. Once we know that, we can assign the forces, the three forces, and then once we've assigned the three forces, then we can answer any questions. When we're comparing, I repeat, only when we're comparing these properties with respect to these two molecules, okay? We're not doing absolute numbers, we're doing relative, which is higher, which is lower. All right, so to put it all together, it says, as you increase the IMF, the viscosity increases. The molecules are being held much tighter with each other, okay? With each other. So that results in the physical property of viscosity going up. The same would be true with the boiling point, because the molecules are being held on with each other much tighter, much stronger, it takes more energy to break up that interaction for them to separate into the liquid phase. And the same would be true for the surface tension. As the IMF increases, the surface tension, for the same reasoning, increases. Where they all go the opposite direction is the vapor pressure. But it's still along the lines of the fact that as IMF increases, the molecules are held onto each other much greater, which means that there's less molecules that are going to go into the vapor phase, okay, on their own at room temperature in the closed container. So its vapor pressure will be much less, okay? All right. Just a few notes about water. We did do the Lewis dot structures of water. Just a couple of things. It does contain the bent geometry. It has two bonding electron pairs and two non-bonding electron pairs. Water is by far the most polar liquid that we have. It will dissolve literally everything. It dissolves it. There's different extents of dissolving. Some molecules dissolve 100%. Other molecules take, maybe, much less to dissolve it. But it does dissolve some of the material, okay? One thing about it, when it comes to solubility, the rule is this: like dissolves like. So polar solvents will dissolve with polar solvents. And that's what it says here. They will mix with other polar liquids. If you think about it, alcohol is a good example, is the polar solvent, polar material. Ethanol is very polar, and it does mix with water, okay? And so because the polarities are similar and like dissolves like. Water has very strong hydrogen bridging forces between them. And they have, being very polar, they have extremely high IMF, very low vapor pressure. The boiling point is pretty high in Celsius, it's 100 degrees Celsius. And it melts, solid going to liquid at 0 degrees. That's the freezing point of water. Very high surface tension. And something unique where we talked about when we talk about density is that water expands when it freezes, resulting in a lower density of liquid water, lower density of water when it becomes ice, which is kind of unusual and rare for that. It makes interesting crystals when it's frozen. Okay. Now, which brings us to what we call a heating curve. Now, what we do here, and we're going to use water as example, and as an example, but it can be pertained to any type of compound. We have a scale here of temperature, obviously in the Celsius degrees. Okay, here we got the 0 point here. And then as we go along the x-axis, we are putting energy into the system. We're heating it up. Okay, so we start off here at 0, 0, 0 temperature, and then we start to heat this thing up. Well, in this area, we have what is the solid phase area, okay? Then we have an area where the solid obviously becomes liquid. And as we continue to add heat / energy, we would then convert that into the gas phase. Now note something interesting. There are a couple of plateaus here, Let me explain what those plateaus, what they are and what's happening there. Okay, and so we start to heat this solid, and again, it could be true for any compound that's a solid, any compound. It starts off in the solid phase, okay, and then we start to heat it, and our temperature rises. Then we hit a plateau. Okay. Now, as we're heating it, all of the energy that we put into the system is causing the molecules in the solid phase to start to vibrate and start to move. Okay, they're still solid. Okay, until we reach what is called the melting point. At that stage, the solid molecules start to be converted to liquids. Okay, so all the energy that got the molecules moving now are now being used to convert the solid property and converting it into the liquid. The result is all the energy that you put into it. Let me clear this up a little bit. From this point here to this point here, the temperature is constant. All that energy, constant temperature, no change in temperature whatsoever. All of the energy you put into that is being used to break up the IMF interaction of that molecule until such time that all of that solid has been converted to liquid. And guess what? We get another rise in temperature as we go across, adding more heat to it. Okay? And guess what? Well, before I leave this, that first point, that first plateau, that is the melting point of that particular compound. And that is the temperature that solid becomes liquid. We call that the melting point. At the second plateau, the same phenomenon occurs. During the rise, it is all liquid. Okay? And being all liquid, it's absorbing the energy until it reaches the second plateau. At that point, when the second plateau is reached, that liquid is now being converted into the gas phase. And all of that energy is being used, absorbed by the liquid, and causing the, again, the IMF interaction to have the molecules separate even further to go into the gas phase. And we reach what is called the boiling point. Okay? Bear with me for 1 second. Somebody is knocking. Bear with me. My apologies to housekeeping. Okay, so we're at the second level where all the energy now is converting the liquid into the gas phase. And that is the boiling point. And notice here, okay, that there is, as you put energy into the system, there is no rise in temperature, okay? So once you got, for example, liquid, and this could have been an example of ice, where ice remains solid until it reaches the melting point, which is for water would be around 0 degrees, okay, Celsius. And then all that ice will be converted when it reaches the melting point, will be converted into liquid. And then at that point, the temperature increases till we hit the second plateau, where this would be for water. If this was water, would be 100 degrees. And so if you take a pot of water and you stick it on the oven, you start to boil it up, turn it on. And once it starts to boil, if you turn the heat up, it's not going to make any difference. It's not going to increase your temperature or make your water boil anymore. Once it's boiled, whatever energy you put into it, and if you add more to it, just wasted energy, because it's any excess energy by turning that fire up, you know, or the electricity up higher is not going to make things go any quicker. So anyway, yeah, 2 plateaus. The takeaway here is that at that plateau, all of the energy that's being absorbed by the system is being used to break up that interaction between the molecules, to break them up, to convert them from one physical state to the other state. Okay? All right, and that's called our heating curve. And so what do we know from the heating curves? The temperature remains constant at that plateau. Okay? All the energy goes into breaking up the IMF interactions. It's not breaking up bonds. Please remember that. It's not breaking up bonds. There are cases, let me clarify, that compounds, when they reach their melting point, they never really reach their melting point. What happens is they get close to it and they start to decompose, which is all right. In some cases, yes, it starts to break up, decompose. But if it's not a compound that decomposes, all of the energy is being used to break the IMF interactions. Okay? To breaking up IMF interactions. That being the case, ladies and gentlemen, congratulations, we're done with chapter 14. Okay? All right. Any questions about that, about IMF? Intermolecular forces. Okay, I'm gonna check my time because the computer's on Kansas City time. So if I go overboard, let me know. I forgot you're in Arizona time. All right. The next chapter, one of the final chapters, very short chapter. Okay, along with the gas chapter. That's what I mean. We'll probably get done with all three chapters here. Is talking about coffee, right? And I'm just kidding. Coffee, what are we talking? Spend all this money for school, we're going to talk about coffee? No, we're going to talk about the solutions, and coffee is the solution. Okay. All right, so solutions. So what is a solution? By definition, okay, a solution is any solute dissolved in a solvent. Now, most of the time we think of solute and solvent as a liquid, and that's true. We deal with that, but solutions can also deal with non-liquids, and we'll have some examples of that. And the solute, well, what is the solute? Well, it's just whatever chemical is present in the smaller amount, where the solvent is whatever chemical is present in the larger amount. And like I stated, most of the time, we'll be dealing with a solvent, a liquid solvent, specifically water, okay? But it's not limited to water, because you can make solutions with non-ionic, non-aqueous systems. This picture here is pretty self-explanatory. It looks like a bunch of bottles of glasses of Kool-Aid at different concentration. You can see that by the shade of the color. Obviously, the far right is very strong, far left, very weak, just based on the concentration. We do use that technique to actually measure concentration using what's called the spectroscopic method, but we're not going to talk about that. Okay, so some examples of solutions. They could be solid, even liquids or gases. For example, when we have a gas in a liquid, like carbonated soda, and that's a solution. Right? We can have a liquid in a liquid, like a drink, alcoholic drink, we have like tonic or water, that is a solution to liquids. Or we can have a solid in a liquid. So if you take table salt, good old sodium chloride, dump it in some water, you have created a salt solution, specifically a sodium chloride solution, okay? But you can also have gas in gas. So our air around us is made up of different types of gases. Some are more concentrated than others. So our air is a good example, where nitrogen, oxygen, carbon dioxide, and all kinds of other gases up there. And even solid in the solid. Okay, most things that we utilize, like the steel in the buildings, steel is not 100% iron. 100% pure iron would be worthless to be used to make structures out of it, because it's so weak. So what is done is we make alloys, and then that is we take iron and add some carbon to it, and that makes it stronger. It gives it a stronger property, and we make things like steel, things like brass. Brass, for example, is a mixture of copper and zinc. And even the gold in jewelry that you're wearing is not 100% gold. It's made up of trace amounts of other materials. We think the strength makes a different alloy. All right, now I had mentioned to you earlier about solubility and polarity. And the classical rule is like dissolves like, okay? And I kind of use a story with my sisters. Growing up, I have 5 sisters, and obviously all of them did the makeup thing. And in the evening, it used to look like a Halloween, because they used to put a white cream, Noxema, to get rid of the paint, or to get rid of the makeup. And so sometimes if they bought certain makeups, if they got water in it, or they cried or something, it rained, it'd start to dissolve and wash. Well, not understanding why then, but now I do, is I'm told that nowadays there's some, quote, hurricane-proof makeup in that no matter how much water hits you, it won't dissolve. And if you think about it, it's probably because that material is a non-polar paint, I guess, for lack of a better term, makeup. Not non-polar, because the water will not dissolve it, okay? And the other makeup where water would, that makeup had a lot more polar character, so therefore water would easily cause it to wash away, okay? And so the point here is like dissolves like. So polar solutes will dissolve in polar solvents, okay? And On the converse of that is nonpolar solutes dissolve in nonpolar solvents. And so nonpolar and polar do not mix at all, okay? Case in point, in this picture here, we all know, we've seen pictures of oil spills in water. They do not mix. It is a big mess. If you like Italian dressing, look at the dressing, the bottle dressing. You got two layers. You have an oil layer and an aqueous layer. They don't mix because what they do is the water layer, the aqueous layer, dissolves the polar material, and the non-polar oil layer dissolves the non-polar components of the Italian dressing. And to get it into your salad, you got to shake it up and form what's called an emulsion. They don't mix up, they just form an emulsion, and you're able to put that in salt. Take that bottle, let it sit for a little bit. What happens? It separates. Okay. All right. Now, when we talk about liquids, we use the term, and liquids that mix, we say that it is miscible. These two liquids are miscible with each other, okay? Be it they're both polar, be it they're both non-polar. Makes no difference. If they are not mixable, we call that immiscible. And so in this scenario, we have an example of a polar solvent and a non-polar material. So the oil and water would be a classic example of oil and water being immiscible, okay? And let's say water and vodka would be miscible because they mix. Now, when it comes to solids, okay, we use the term, when solids placed in a liquid, we use the term soluble and insoluble. So if a solid dissolves, it is soluble. And if it doesn't dissolve, it's considered insoluble. But remember, even though it's considered insoluble, a small percentage of it still goes in solution. When we are dealing with ionic compounds, normally we're dealing with a water and aqueous system, okay? So we use the solubility rules to find out. But it is feasible to also to have non-polar solvents like an oil, like vinegar, like vegetable oil or olive oil. And we have material that will dissolve in those type of oils because they have non-polar characteristics, properties. Okay, so we have a table here. Here on the first column, we have the solvent. And then this second, third, fourth, and fifth, we have a solute. And we're asked to determine, will the solutes dissolve in the solvent? Well, to answer that, we have to determine the polarity of everybody, okay? NH3, we talked about that. It is polar, okay? Now, if you look at HCl, we also talked about that. Oh, let me back up, I'm going the wrong direction. But we have C12H26. You may not know what it is, and that's okay, but I hope you can recognize that you're dealing with simply carbon and hydrogen, specifically 12 carbons and 26 hydrogens. That should tell you it is a hydrocarbon for one, but the second point, it should tell you it is basically a non-polar species because there's nothing but carbon and hydrogen there, okay? And then we look at Br2, which again, it's diatomic. And what do we know about all diatomics with respect to polarity? They are non-polar, okay? So a bromine is nonpolar, the hydrocarbon is nonpolar, and ammonia is polar. Okay. All right, so now we look at the solutes and we have to define each one and determine their respective polarity. HCl is polar, and we got hydrogen and chloride. We have a dipole, a permanent dipole between hydrogen and chloride because we have two different electronegativities, chloride being much stronger than hydrogen. I2, iodine, is diatomic, therefore no question about that, nonpolar, okay? PCl3, well, you may not be sure, so what do? you know, given that P is primary, let me change the color here. The phosphorus is the central atom. You can go through the Lewis dot structure procedure. And when you do that, now I gotta change the color back. You end up with phosphorus bonded to 3 chlorides, much like ammonia is. Okay, and you end up with this. And then you end up with a lone pair. Now you would think, okay, I have 3 polar bonds. Okay? And a lone pair sitting here. Okay, you can take what I just stated, that lone pairs, always you got a lone pair in there, you got a polar molecule. You don't have to go any further, but you can go further and analyze it, and you realize that because you have a lone pair, the dynamics, the geometry is such that the bond angle here is brought in, which causes the polar bonds not to cancel out, okay? Not to cancel out, so I have a polar species. But like I stated, you got lone pair in the central atom, you have a polar molecule. And then the solute here, 1 carbon, 4 hydrogens, just like C12H26, it is a nonpolar moiety. So there you go, it is nonpolar. So now you go through the exercise of just checking the polarity and determine whether something is soluble or not. And the first pair would be yes, obviously because you got 2 polar molecules. Okay. No, simply because you got a disparity in polarity. Similar in polarity here, and that's got a yes for next set, and no for the next set because of dissimilar polarity. The hydrocarbon and the polar hydrochloric acid, we definitely no. Yes for the iodine, no for PCTL3 because of polarity, yes for CH3. Okay. No for bromine and HCl. Yes for iodine because of the similarity of polarity. No for PCl3. And yes for the nonpolar CH4. Okay. So to determine whether something would be soluble or not, in the solute versus the solvent, we need to determine the polarity, okay? And sometimes if we didn't know what it is already, we need to actually go back further and figure out the structure based on the Lewis doctrine. Okay, so miscible and immiscible, we talked about if they're liquids, the term would be either miscible and immiscible. If they're solids, it's going to be soluble or insoluble. So very quickly we can see this pair is miscible, this pair is immiscible, and immiscible because of differences in polarity, miscible again because similarities in polarity, soluble because we're dealing with a polar solvent and trying to dump it into a polar solvent. So yes, it would be classified as soluble. Okay. Now bear in mind, I was asked a question once, but let me clarify this. When we talk about soluble, anything has limitations as far as solute and solvent. Okay. There's limitations with the amount that you can put in the solvent. For example, I have a teaspoon of table salt, sodium chloride, and a gallon of water, no problem. I dump it in, all that sodium chloride will dissolve. However, what if I got 5 pounds of sodium chloride and still got 1 gallon of water? Well, yeah, the large majority will go in solution, but there's going to be some of it that will not because it's not insoluble, it's because the solvent, the water, has a limited capacity to dissolve material. Okay, so and nothing to do with polarity, but has to do with capacity amount. Anyway, so polar solvent, yes, soluble. Insoluble when it's polar and nonpolar solvent. Good example, further down the road, I'll show you. Insoluble is non-polar solid versus a polar solvent, insoluble. Ionic compound and polar solvent, check the solubility rules to be either classified as insoluble or soluble. But keep in mind, I can't overemphasize, even though it's classified as insoluble, there's a small amount still going in solution. And then insoluble if it's a non-polar solvent, and ionic compound. Classic example, throw some oil on a pan, you're frying some eggs, if you throw table salt in that oil, it is not going to mix, okay? We have an ionic compound that will not dissociate and break down in a non-polar solvent such as oil. The dissolving process, not much to say. We talked about this briefly, where you get the sodium ion. This is also related to the IMF, ion dipole IMF that we discussed earlier, where you got sodium being immersed completely by the water molecules. You got a full charge positive on the sodium, and then the partial negative of the oxygen of water is then attracted to it, and it totally surrounds it completely and solvates it. On the opposite end, on the partial positives end of the hydrogens, you will find that this was the corresponding anion for whatever salt this was. It could be chloride, for example. Okay. Now, we had dealt with the concentration before. In this one, we were talking about pH. And I mentioned we'll talk about it. pH way back when, remember, it was hydrogen proton concentration. We had it in brackets. And we listed it as in brackets, so to refresh your memory, we had H plus, and then we used the brackets, and this is the concentration unit. Well, at that time we said it has units of moles per liter, okay, and that was molarity, okay? And we're going to talk about how to calculate that. That is one concentration fact unit that we're going to use. The other one is called mass percent, and that is the weight of your solute divided by the total weight of your solution, okay? Total weight of the solution. So it's simply a weight scenario, and then we multiply that by 100 to give us 8%, mass percent. Totally different from molarity, because we first need to calculate the moles. So therefore, if we're given grams of a compound, we have to determine the structure of that compound, the formula, I should say, of that compound. So therefore, we can determine the molar mass of that material. So therefore, we can determine the number of moles. And then the volume, we take the volume, we put it in. Sometimes the volume is in liters, units of liters. But occasionally you might be given units of milliliters, so you need to convert the milliliters to liters. So remember, there's 1,000 milliliters per 1 liter, okay? You need to be in liters. You need to be in moles and in liters for molarity. All right. So let's work on mass percent, or mass percent. By definition, it is the mass of the solute, okay? Mass of the solute divided by the mass of the solution. Now, the mass of the solution is the total mass of the solute plus the total mass of the solvent, okay? So in this example, if you were to take 15 grams of potassium nitrate, we don't really need to know the formula of potassium nitrate, okay, because we're asked to calculate the mass percent. So we just need to know the weights. We're going to dissolve it in 135 grams of water. And we're asked to calculate the mass percent. Well, back to the equation. It is the mass of the solute, which is 15.0 grams, divided by the mass of the solution, which is the sum of the 15 and 135. And we multiply that by 100. And that tells us that we have a 10% mass percent solution when we dissolve 15%, 15 grams of potassium nitrate in 135 grams of water. This is the same thing for those of you who work in the medical field and may be familiar with saline solutions. Saline is nothing more than sodium chloride dissolved in water, and it's a 0.09% mass percent, small amount. And it has to be that way. The saline solution at that percentage keeps their cells from either, when we inject the liquid in their cells, they're either gonna coagulate, break, squeeze up, or they're gonna blow up. Okay, and this one keeps the osmotic pressure constant, so it won't destroy our cells too bad. So anyway, that is how we calculate the mass percent. Now, occasionally, now, sometimes, you might be given the weight of the solute, you'll be given the percentage, but you don't know how much water to use. You need to calculate that. So when that happens, you have to set up an algebraic equation. Okay, so we got a little bit of algebra here, not very complicated. A little bit of algebra so we can solve for how much water we need to use to make whatever percentage you've been asked to calculate. Okay. And an example will be here. So they're asking you, well, how many grams of water are needed to make a 5% saline solution, which is if you're using 10 grams of salt. So for some reason I got 10 grams of salt there. I've been asked to make a 5% solution for whatever reason. And I need to determine how many grams of water I need to utilize. Okay. So let's assume you don't have Google, you can't Google it. So we need to calculate it. All right, so what I do, I set up my equation as follows, okay? I know I need 5% right here, okay? That's my 5%. I'm given 10 grams of solute, and what I don't know is how many grams of water I need to use. And so all this times 100. So that is my algebraic equation. And what I need to do is to solve and to take out the x, okay? Now, when I used to teach algebra, I said, I used to tell my students, there's a lot of ways to solve for x. And the way I'm going to show you is just one way. It's not the right way. You can do it different ways, that's okay. But the point is, get to that number you're looking for, okay? So what the book did here, I would have done a little bit different, but I'm going to follow the book, is they first take the whole quantity 10.0 plus x, that whole quantity in the denominator, and multiply both sides of the equation to get that. Okay, see what they did? So they did over here, they took 10.0 plus x, that causes this to cancel out, and then they multiply the same quantity over here, okay, to give you that here, okay? And that's how they got rid of the denominator. Then, now you can go in multiple ways here. You wouldn't be wrong to spread this one out. You can go here 10 times 5, and then 5 times x, you go 5x, and multiply this and go there. You can do that route, okay? Or you can do what the book did, and they went ahead and multiplied the 100 times 10, okay? Then, instead of distributing on the left, they got to this value. And how they did that was simply divide both sides by 5. Okay, to give you this, and bam, you got 10 plus x is equal to 1,000 divided by 5. Okay, work out the right side. So you got 10 plus x is equal to 200. Now you got x pretty close separated, and you just subtract by 10 on both sides to solve for x, okay? And you end up with 190 grams. Now the reason they put it in scientific notation was because of sig figs, okay? Sig figs, these numbers are constant, exact numbers, where this is not. Okay. So you got 3 sig figs, your answer should be in 3 sig figs. And here's a scenario where, you can't put 190 in 3 sig figs. And somebody would say, well, what if you put a decimal point? Well, the moment you do that, a decimal point, you technically, yes, you got 3 sig figs. You could put a decimal point, but then you got to add a 0. I mean, personally, I would accept that. That's 3 sig figs in my book. But the mathematician in me says, no, you got to put a 0 there. All right. So when there's any ambiguity, when in doubt, what do? You put it in scientific notation. There's no question there. No question there. 3 sig figs is 1.90 times 10 to the second power. Okay. Now, how do you know that number is correct? Well, you take that 190 and you stick it back in there in the original equation and run through the mathematics, and this whole right side should end up as 5.00. So 5.00 equals 5.00. That is a true statement. So that number is correct. And so, in other words, another way to say this is, if you take 190 grams of water and you dissolve 10 grams of a salt, you end up with a 5% saline solution. Okay. Any questions about that one? All right, well, that brings us to the last concentration unit, and that is molarity, which by definition is moles of solute divided by liters of solution. Okay, so here you're being asked to calculate the molarity if 9.9 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay, so to do this question, well, the first thing you need to know is you need to know the formula of potassium bromide. Okay, right here, potassium bromide, because without it, you cannot calculate the molar mass, because you need the molar mass to calculate the number of moles. Okay, so what we do, it's written out, so we're going to go from the name to the formula, and as I stated, write the respective atoms in ionic form. Potassium, we know, is in group 1A. Okay, has a symbol K. And being in group 1A, the ionic form, it has a +1 oxidation number because it's in group 1A. The bromides are in group 7. When they become ionic, they gain 1 electron, so therefore they have a -1 charge. All the halides do. So that is the ions being utilized. There's simply a 1-to-1 relationship here, so I can put them together, and that is the formula for potassium bromide. Now I can look up from the atomic, look up the atomic weights for each one bromide, 1 potassium, tally them up, and that would give me the molar mass for potassium bromide. Once I know that, okay, which is 119 grams per mole, I set up the molar mass with grams in the numerator because I want grams to cancel and I want moles at the end, okay? Now notice the numbers were not truncated. Don't truncate, don't figure out the sig figs until you're done with the full calculation, okay? So carry the number out as far as you want, you know, maybe a good 6-7 digits beyond. Okay. Then you divide by the volume, in this case, 2.5 liters. So now the molarity of this solution is 0.0336 moles per liter. Okay? It means every liter in this solution contains 0.0336 moles of potassium bromide. And that occurs by dissolving 9.99 grams of potassium bromide and dissolving it to exactly 2.5 liters of solution. Normally, when we make these type of solutions, we use these what are called volumetric flasks. They have a 1 mark for a specific volume. And so we pour the solid into these flasks, and then we bring the water up slowly and carefully to the meniscus to be right at that mark, because that mark is the exact volume. And even that doesn't give us the exact concentration. A lot of times we're going to take one more step to verify it and calibrate it. But that's how we do it in the lab. Okay, so now let's do one more. I think we're done here with this chapter. All right, here we calculate the molarity of sodium phosphate if you dissolve it in water to make 255 milliliters of solution, okay? So we're taking 5 grams of sodium phosphate, and we're gonna take, dissolve it with 255 milliliters of solution. Remember that molarity by definition is moles per liter. We are given milliliters, so we need to convert that to liters. So remember, there's 1,000 millennium in a year, right? So there's 1,000 milliliters in 1 liter. You need that. We're also going to need the formula for sodium phosphate. Well, we know sodium is in group 1A, so it has a +1 charge as an ion. Phosphate, that should direct you to the polyatomic ion table. And when you do that, you should end up with this particular formula, okay? PO4 -3, okay? That means we need 3 sodiums for every phosphate. Its formula is Na3PO4, okay? Now you can figure out the formula weight. We got 3 sodiums, 1 phosphorus, 4 oxygens, okay? Multiply each by their respective atomic weight, tally it up, and you should end up with the molar mass for potassium phosphate, okay? Which that adds up to 163.94 grams per mole. And like we did earlier, remember when you're starting grams, you want to go to moles, guess what? You're dividing by the molar mass. You're dividing 5.0 grams divided by 163.94. Grams cancel out, leaving us with moles. Again, carry it out as far as you can, 4 or 5 digits out there, okay? Then we need to convert the 255 into liters. So we have set up this conversion factor like we've done before. Nothing new here. That puts us in liters. If you recognize you can just simply move the decimal point over 3 positions, you're good to go. That's fine too. But if you forget, you know, go ahead and do the math. All right, now you take the moles divided by the volume. Okay, keep an alert that, you know, keep a track of your sig figs. Okay, we got 2 sig figs here, 3 here, right? The atomic weights are not, molar mass are not used for determining your sig figs. So your final answer should have 2 sig figs. Okay, so that becomes 0.12 moles per liter. Okay, so taking 5 grams of sodium phosphate and dissolving it in 255 milliliters gives you a final molarity concentration of 0.012 moles per liter. Moles per liter. You might ask, well, why are you making these solutions? Well, a lot of times when you're running reactions, instead of having to weigh out the amount that you need, you can actually, now you have a solution with that molarity, and that molarity says, okay, for every liter of solution that I take out, I'm taking out 0.12 moles of sodium phosphate. And so now I can play, take volumes out because it's the sodium phosphate dissolved in solution. I can take volumes of that solution to take out the specific number of moles that I need. Okay. All right. Now, that being said, don't forget assignments, obviously, homework, and so forth. There is a practice final exam on the website. It's a reminder, so it's a good resource for you, okay? That being the case, congratulations, you have chapter 15 is complete. And we are going to actually finish all the chapters because the last one is not very long. So I tell you what, I have, what is it? It is 2:20 in your time, right? 2:20. Let's take a quick 15-minute. I got 4:35 my time. That should be 2:35 your time. And then we'll come back, knock out the last one, and we'll be good to go for the semester. All right, any questions? All right, well, I'll be back here in 15. Okay, guys, too bright. I'm back. Now, this last chapter, as I stated before, it's not going to be on the final. The only thing you have is homework for it. It's one of the things that's required by Maricopa to talk about gases, but it's so late in the semester that it really, I just don't incorporate it in the final exam, because you now have enough information for next exam. And we're going to briefly talk about these gases. It's probably about 8-10 slides. Some mostly calculations, okay? Mostly calculations. And then after that, we'll be done. So if I get done with this today, that means on Tuesday, I won't be here lecturing, but I'll be here. I will be on the road, but I will stop to see if you have any questions. We can go over the questions that you may have concerning the other previous chapters. I'll hang around for a good half an hour, 45 minutes. If nobody has any questions, I'll shut it down and go back on the road. And then I'm back home on Thursday. I'll open that up again. I'll be here for any questions, Zoom that is, because that is the final on Thursday, but I'll be here during the regular time. If you have any questions that you need assistance with. So these last 2 meetings will be more like a study, session, if you will. All right, so let me begin with the gases, okay? What about the gases? Well, let's talk about pressure. Pressure is a measurement, okay? It is a force per unit area exerted by gas molecules colliding against the walls of the container, okay? Now, we can increase the pressure by increase the number of collisions, hit more hits. One way of doing that is just add more gas to the container. Your flat tire, for example, you put air in there, pressure goes up. More molecules are in there, more hits on the wall, pressure goes up. We can increase the energy of the molecules in there. If you were to measure the pressure, your tire pressure before you drove it in the morning, it would be, let's say, 32 degrees PSI, 32 PSI, I should say. Run it for a couple hours on the road and then measure its pressure, you would see that pressure has gone up because of the heat, causing more molecules to be bouncing up against the walls and pressure goes up, okay? There is no pressure in the vacuum because there's no air molecules in the vacuum. It's just empty void of anything. Now, with respect to atmospheric pressure, that is the force of air that's hitting on us. And that is a lot of pressure that we don't really feel. But I want to do a quick calculation to kind of put it in perspective, okay? Let's say that if you take a 1 meter by 1 meter distance right around you, for example. So if you're right around you and you measure 1 meter by 1 meter, okay? So we've got 1 meter here, 1 meter here. Obviously, we've got 1 square meter, okay? Now, go up, same unit, up into the air by 10,000 meters, okay? 10,000 meters. Now you have 10,000 cubic meters of space above you. You're sitting here. Okay, now that air is filled with air molecules. 10,000 cubic meters of space straight up. Now, if we were to just do a rough calculation and say that the density of the air is roughly 1 kilogram per 1 cubic meter. Okay, now we can take that density of air in those units and multiply it by the 10,000 cubic meters. Notice our meters cancel. We have approximately, because obviously it's a rough calculation, 10,000 kilograms of air hitting on your head. Okay, 10,000 kilograms. That's a lot of pressure. That's a lot of air. So you might ask yourself, how come I'm not squished like a pancake? Anybody have any idea why you're not squished with a pancake when you got 10,000 kilograms of matter hitting on you? Now, if you went 10,000 meter down in the water, yeah, a different situation. You would be squished like a pancake. Okay. Well, the reason you don't cave in where we're at here is because we've adapted as human beings to live with that pressure. So we have one of the laws of physics where there's an opposite force. When there's a force given onto you, there's an opposite and equal force in the opposite direction. So within us, we have an internal pressure that counters that 10,000 kilograms of pressure, and that's why we don't squat in. And but if we go under 3 or 4 miles underground in the water, that's a different situation. We will get crushed. But there's plant life down there in deep water, okay, because they've acclimated to that amount of pressure and they survive. All right, so that was a lot of pressure on you. Okay. As we climb, obviously there's less pressure because less air up there, okay, less matter hitting on you, pressure goes up. Now, how do we measure pressure? Well, we use what's called a barometer, okay, and we have a barometer that's filled with, this one here, this example is filled with mercury. And we got an open end here, and as you can see, as the atmospheric pressure goes down, it pushes on the mercury in, and it causes the mercury to go up to 2, okay? Over here, we have a scale that goes from 0 to 760 millimeters, okay? So we measure the distance. So in this case, this is measuring 760 millimeters or 29.92 inches. And so as the outside, we get a pressure, our atmospheric pressure increases or decreases, this pressure reading goes up and down proportionally, okay, depending on the pressure. Now we use mercury because mercury is a very dense metal. We can use other liquids. You can use water, but the only problem, because the density of water is so small, that we require a tube that's about 32 feet long. It would give us the same type of reading, a different scale that is, but it'll still function. But mercury is a good, well, so I don't know if they're still using it as much, different tools now being utilized, but that's how we measure that barometer. That's how barometer is measured. Now, what kind of units are we dealing with? Well, we have a few units. We have atmosphere, which we talked about. So at 1 atmosphere, it is specifically 762 torr, or 760 millimeters of mercury. Torr is another unit that is utilized. The English unit will be PSI, pounds per square inch, okay? So that would be equivalent to 14.7 PSI, pounds square inch. So we have 4 different conversion factors, and we can go from atmospheres to PSI to millimeters of mercury and so forth. Now, for example, some type of these conversions here, a diver's tank is set at 4,400 PSI. Question is here is convert that number to torr, atmosphere, and millimeters of mercury. Well, we can do that just like we've been doing with all the other conversion factors. We have a ratio that we can utilize and set it up depending on the units we're given. And so if we have 4,400 PSI and we're looking for atmosphere, we set it up so that 14.7 PSI is in the denominator, so we can cancel it out, okay? So that corresponds to 3.0 times 10 to the second atmosphere, which then corresponds to 230,000 torr, which is also the same amount of millimeters of mercury, okay? So this exercise is simply just the conversion of units from one set to the other. All right, now with respect to when we deal with gases, we deal with 1, pressure, volume, and temperature. Those are the 3 variables, okay? And what we know is this, that if we increase the volume of a gas in the container, guess what? The pressure decreases. Okay, now how does that work? Well, let's say if you have your tire pressure of your regular car tire, 32 PSI, okay? It's set up with the X amount of matter in that, there's an X amount of matter in that tube, that tire. If you were to take all of that air in your tire and transfer it over to, say, another tire, let's say it belongs to an 18-wheeler truck, well, what happens? The pressure of that truck is going to be very low because there's not enough. You increase that volume. So that volume now is much bigger for the 18-wheeler tank than it was for your car. So the pressure decreases very much so. Okay, you will no longer be at 32 PSI. You'll be much lower, literally 0 based on the volume of that 18-wheeler tire. Okay, now if you take the temperature and you increase it, the temperature, the pressure goes up. Again, the example I used earlier was the fact that if you take your car, measure the pressure before you leave in the morning when it's still cool. Let's say it's set at 32 PSI. Run it for a couple hours. The friction of the vehicle will cause your tire temperature to go up. Stop, measure the pressure. You will find it to be much higher than 32 PSI. So the temperature, as you increase the temperature, the pressure increases. Now, what happens, what is meant here is the relationship. In example number 1, when the volume increases, the temperature decreases. That's an indirect relationship or inversely proportional, okay? So one variable goes up value-wise, the other one drops. In the second example, if you increase the temperature, the pressure also goes up, okay? And so that is a direct relationship. So you have an indirect and a direct relationship. Yeah, if you increase the number of gas molecules, the pressure goes up. Yeah, pretty self-explanatory. You put air in your tire, guess what? Pressure goes up, right? You're adding more molecules, more atoms, more matter into your tire, pressure goes up. That also is a direct relationship. Increase one variable, the other variable goes up. Okay? And so we have this direct, indirect relationship. When it comes to pressure and volume, there is an indirect relationship because as we increase the volume, the pressure drops and vice versa, okay? When it comes to pressure and temperature, it's a direct relationship. Increase the temperature, pressure goes up. And the same is true with increasing the number of atoms with the pressure. There is a direct relationship there. Increase one variable, the other variable goes up, okay? So with that information, we ended up with specifically 3 gas laws. The first gas law is called Boyle's law. And what that says is this. Now, the subscripts 1 and 2 represent a set of conditions initially, represents 1. And for 2 are the final conditions, okay? So you do something to your system, you start off at a certain condition, and then you measure those things after you're doing whatever you're doing, and that's the second set of conditions. So what Boyle found out and determined was when you take the initial pressure and you take the initial volume, okay, and you do something to it, that specifically the product, when you multiply the pressure initial times the volume initial, that is equal to the quotient again of the pressure final times the pressure final, the volume final, okay? That same quotient occurs. That's the product of the multiplication step that you do. Now notice in Charles Boyle's law, the 3 variables are pressure, volume, and temperature. Here, temperature is not even in the equation. So what they've done is they did these changes and they held the temperature constant. You hold the temperature constant, that temperature comes out of the equation. So that's what you end up with, that relationship P times P1 times V1 equals P2 times V2. Think about this. I got 4 variables. I will always be given 3 variables. I can solve for the 4th one, okay? Now, Charles come along and he determined that if you take the volume 1 divided by the temperature 1, that is equal to the new volume divided by the new temperature, okay? So the quotient here is equal to, the quotient initial is equal to the quotient final. Okay. Notice there's no pressure involved here, no P. So in that case, pressure was held constant. So a set of experiments were done holding the pressure constant, and the only measurement that was involved was that of the volume and the temperature of the system. Then you got Gay-Lussac's law, okay? Also dealt with the quotient, specifically the pressure over temperature. The pressure 1 initial divided by the pressure 1 initial is equal to the new quotient of pressure 2 divided by temperature 2. Okay. Notice here that the volume was held constant. So there's no mention being constant. Since that variable is held constant, it just drops out of the equation. You need to worry about it because it's held constant. Okay. So what that does here is the following. You have what's called the combined gas law. That includes all the variables. and their relationship to each other, okay? Under the initial conditions, and then the final condition designated as a subscript 1 and subscript 2. Okay. Now, under these conditions, we are under STP, standard temperature and pressure, which is 1 atmosphere and 0 degrees centigrade. When we're doing all these variations, when all the experiments were done, everything was held under STP. Now, some constraints about using these equations, okay? Constraint number 1, temperature, if you're using temperature, must be in Kelvin. Okay, that is, so take your temperature in Celsius and add 273. Now the volume, if you're using volume, regardless of which, like Charles' law or Boyle's law, if you're using that or the combined gas law, make sure the volumes on both sides of the equation are in the same units because they're going to cancel each other out. So make sure. So don't do one side as milliliters and the other side as liters. Just keep them both the same units. Pressure, same is true for pressure. Pressure on both sides of the equation must be also in the same units so they can cancel out correctly. And then reading the question, identify based on the question, who are the initial conditions, and then what are the final conditions you're trying to strive for, okay? If there's no mention of pressure, volume, or temperature, it remains the same, then they cancel out and you can remove them from the combined gas law back here. So you can remember the combined gas law equation, read the question. If one of these variables is not mentioned, let's say the question says, and pressure is not mentioned, and guess what? Pressure cancels out because pressure is held constant. And who do you have? You have Charles' law, right? This is Charles' law. Now, if you look at the questions given, and let's say volume is held constant, well, the volume's being constant cancel out. Now you have Gay-Lussac's law. Okay? And then finally, of course, if the final example would be if temperature is held constant, well, the temperature then cancels out, and then you have Boyle's law that you're working with. Yeah, from my perspective, I just start with this, look at the question, and then whatever it's not being mentioned, I can just remove the variable, okay? That's probably the simplest thing to do. And then don't forget about this information concerning calculation. For example, a sample of carbon dioxide. Oh, I have a question. Give me one moment. With just the volume, whatever the volume is given. Amy had a question about the volume. It could be whatever volume you're given. You'll be given a specific volume. It may not even mention what type of container, just be given a volume. And just make sure that the volume on both sides of the equation are the same units. So if the question says millimeters to begin with, and you ended up with liters to end up with, well, you're going to use stick with one, either convert everything to milliliters or convert everything to liters. Okay. All right. So here the question: the sample of carbon dioxide occupies 2.25 liters at 758 torr. Find the final volume if the pressure is decreased to 698 torr. Okay, and so here we're dealing with temperature constant, right? Temperature is not even mentioned. So, I mean, let me go back to the, I can use this, the combined gas law. Okay, I read the question and there's no mention of temperature. Okay, so I can assume that the temperature is held constant. All right, and so now I have, that's the gas law that I'm working with. Okay? And they're asking you to find the final volume, which will be V2. So I'm solving for V2. So I rearrange the equation. So now it becomes, what I'm looking for is V2. Okay. And so I can divide through with P2. I end up with V2 is equal to P1 times V1 divided by P2. So that's my final equation I'm going to have. Now it's a matter of plugging in numbers. Okay. And so I end up with 2.44 liters. .44 liters. All right. Oh. Now here it says a sample of krypton occupies 3.91 liters at 105 degrees Celsius. Find the temperature in Celsius of the gas if the volume is changed to 6.05 liters. Okay, what two things here. I'm looking at the question. They give me liters, they want me to find out temperature. So what does that mean? That pressure is held constant. Right? So I can take the combined gas law and it becomes V1 over T1 divided by V2 over T2. Okay? Second point, I'm given the temperature in Celsius, so I need to convert that. All these calculations using the gas equations required to be the temperature in Kelvin, so I need to convert 105, convert that to Kelvin, so I simply add 273. The volumes are both in the same unit, so they're good to go. So now it's a matter of plugging in the numbers, okay? And changing the temperature of 105 to 273. At 273 to that, it gives me 378, okay? I do the calculation, I end up with T2 being 585 Kelvin, but the question asks to give the answer in Celsius, so I got to subtract 273 to convert that Kelvin temperature back to Celsius. All right. Here's another one. It says a steel container filled with nitrous oxide at 50 atmospheres is cooled from 25.5 degrees to negative 40.8. So it's getting colder, okay? So they start at room temperature ballpark and they bring the temperature down. It says calculate the final volume. Okay, so here, the final pressure, calculate the final pressure. So that means that volume here is being held constant. We want to know the final pressure. Okay, so we got P1 over T1 is equal to P2 over T2. Okay, solve for P2. Remember, the 2 represents the final conditions, and we're looking for the final pressure. So we're solving for P2. So our equation is given as follows. So we plug in the numbers, okay? Keep it in mind, temperature needs to be converted to Kelvin. So I have 273 to those temperatures, okay? So we end up with a pressure of 11.7 atmospheres. 11.7 atmospheres, which makes sense when you think about it. When you freeze something, you know. Don't believe me? Take a balloon, blow up a balloon, stick it in the freezer, and tell me what happens when you take it out after about an hour. You know, you might notice that it shrunk, and that means the pressure. The molecules have. You didn't lose any molecules. You just slowed the molecules down. They're not bouncing up against the balloon very much. Okay, they lost some energy, so the pressure will go down. If you were to measure the pressure, it would be less. Okay, in this case, the nitrogen gas sample occupies 50.5 milliliters at negative 82. Don't forget about these negatives. Sometimes you might think it's 82.8, but you know, there's a negative there. So this is some old stuff. We're at negative 82.8 degrees Celsius, and it has a pressure of 1250 torr. Question is, what is the volume at STP? Okay, so let's think about this. Here, you're going to use all of the combined gas law. Why is that? Well, look at the initial conditions. The nitrogen gas sample occupies a volume of, okay, so V1 is there, and a temperature of T1 is there, and a pressure of P1 is there, okay? What is the volume at STP? So the new conditions now are, we're looking for V2, which we don't know, standard temperature, okay? Well, P2, it is 1 atmosphere, okay? And T2 is at 0 degrees Celsius, right? Are not these the conditions of STP? Okay? And so in this scenario, none of the variables are being held constant. They're all being used. Okay, so we're only calculating for volume 2. So we're using the combined gas law. And what do we need to know? Well, we need to make sure everything on the volume, well, the volume doesn't make a difference. We can keep it at milliliters. We're good to go there. Temperature has to go to Kelvin. So the negative 82 goes to Kelvin. All right. And then the pressure torr, well, you have a choice. You're given torr, but STP is an atmosphere. So whichever you want to do, you can convert the torr to atmosphere or go to the atmosphere to torr. Choice is totally yours, okay? As long as the units are the same. And then with that being said, plug it in this scenario. The 1 atmosphere was converted to torr, okay? Real simple, 1 atmosphere equals 760, hence you got 760 torr. The volume obviously is millimeters, the temperature is at Kelvins, and then our final volume becomes 119 milliliters. Okay? And you ask yourself, does that number make sense? Well, give it some thought. Think about it. We are at negative 82, and then and we're ending up at STP 0 degrees. So we're getting warmer, aren't we? Right? We started at 0. We end up at 0. We start off at 82, negative 82. So we're getting warmer. So that means at that volume, we anticipate, like any balloon, gets bigger as the temperature is going up. So yeah, that number looks reasonable and looks consistent with what we would kind of calculate. All right, so that's an example of using the combined gas law, using all the variables. Okay. Finally, the last gas law to use is called the ideal gas law. In the combined gas law calculations, that examples are like as follows. We start off with initial conditions, and then we're trying to do calculations of the final conditions, okay? That's what we're doing. In this one, way back when, we have stated that unless you were at STP, we didn't know the volume. We just took the container's volume. We didn't know what it was, okay? But then we introduced the idea of 22.4 liters per mole only if we were at STP. That's when we had a definite volume. Prior to that, we had no definite volume. Now, we can calculate a definite volume using this gas law here. And is P, which is pressure, V, which is volume, N, which is the number of moles, R is a specific constant with specific units, and T is in temperature, okay? So pressure has to be in atmosphere for this one, and I'll explain why. Second, volume is in liters, okay? N is in moles, there's only one unit there. And R is a constant. And now you can use this constant in a variety of different units, but if you do, you got to make sure your pressure and volume are in the same units, okay? This constant, 0.8208, is in the units of liter atmospheres per mole Kelvin. That means if you use the ideal gas with this particular constant, the units must be in liters, atmosphere, and temperature must be in Kelvin. Doesn't mean that you can use other units, but you got to make sure you're using the correct constant, okay? Constant. And then temperature, as always, will be in Kelvin, always in Kelvin. All right, so we use this law to find variables about a gas, okay? If we know, pressure, volume, moles, and temperature. The other combined gas law is we use those equations when we're taking, we know the variables, but we're changing the conditions, and we need to calculate the new variables, the value in the new variables, okay? All right, for example, what is the volume of a gas if the pressure is 3.56 atmosphere, the temperature is at 25.6 Celsius, and there are 33.35 grams of carbon monoxide present, okay? So knowing the ideal gas law, we need to convert some of these variables. Temperature must be in Kelvin, so we take 25.6 at 273. Okay? Pressure is fine at 3.56 atmosphere, but if it was in torr or anything else, or PSIs, we need to take that and convert it to atmosphere. Okay? And then grams, we need to convert to moles. And so we know that carbon monoxide has a molar mass of 28.01. So we take 33.35 divided by the molar mass of carbon monoxide, and that consists of 1.190646. Keep the digits until you're done with all the mathematical function, okay? And that includes with the change of calculation of your temperature. All right, and now plug it in. And so we're solving for volume because the question is, what is the volume? Right? So now we plug in using that gas constant of 0.08206. And then our answer is the volume is 8.2 liters, okay? All right, bear with me for 1 second. I need to do something real quick. Somebody's at the door. It'll take about 2 minutes. Okay, I'm back. And so here, by putting in the variables, we know that we take 32.35 grams of carbon monoxide, and we bring it to a temperature of 25.6 Celsius, and we're at a pressure of 3.56 atmospheres. It would have a volume of 8.20 liters. Okay? That's from the ideal gas law. That, ladies and gentlemen, brings us to the end. Congratulations, you've had 16 chapters of chemistry in, 8 weeks, a little bit less than 8 weeks, quite a bit of stuff. Hats off to you, because the summer session, you really are hit hard with having a lot of assignments to do. We normally spread it out over 16 weeks, and here we're going to spread everything, crunch it down. So anyway, just a few things. A reminder, chapter 16 won't be in the final, but it does have homework. What else? The final is next Thursday. The other aspect is if you have any assignments that need to be turned in, yeah, please get them all turned in before the 21st. And if you are wanting to go back and do, if you only done one of the homework assignments and you want to go back and to improve your score, by all means, do your second attempt. If and only if you turned it in initially at the correct time at the due date, then I will, if it is a higher score, I will obviously take off the penalty that Hammond puts in it because it thinks your second attempt is late. Okay, so, and just let me know, please let me know what the homework is. If you just tell me the homework, I don't know anything specifically you're talking about. And then, of course, the nomenclature, you still have to next Thursday, you've not completed that, to continue it. And you also have the option to continue if you are at the 80 and you want to try to improve your score. Feel free to go in there and attempt it as many times as you want, because candidates will keep the highest score. Okay. Other than that, it's been a pleasure. I will be here Tuesday, as I stated. I'll be on the road. Where? I'm not quite sure. I'll get there. You know, I'll probably be in New Mexico again someplace. So we'll set up shop someplace, open up the lecture. And if you have any questions, feel free to drop by. If you don't, that's okay. You're good to go. If no one shows up, I would say within 45 minutes, 30 minutes or so, I'll go ahead and shut them down. But and then continue to get on the road. And I should be home by next Thursday also. And also next Thursday, I will open up Zoom. So if you have any questions for the final or anything at all. So anyway, if I don't see you, take care. Have a good, safe rest of your summer. And good luck on that exam. The exam the final exam consists of 60 questions, all multiple choice, okay? You will have almost 2 hours. I think it's an hour, 50 minutes. And so give yourself plenty of time to get that completed. All right, any questions? Are you, I got a question here. Are you opening the exam? The exam will be open, the final exam will be open on Thursday, 7 a.m. And on Thursday at 11 p.m. Exam number 5 this weekend will open up on Friday and close on Saturday. Is that the one you're talking about, Natasha? Okay, yeah, it will open up Friday and then close on Saturday, just like the last one. But the final is one day, Thursday. And if you guys, for some reason, some people need to take it early, maybe you're leaving, going out of town, whatever. If you need it earlier, I can't do it later, but I can move it earlier. If you do need that, just shoot me an email and I will open it up for you earlier if you need that. Okay. Any other questions?
Yeah, Dr. Fred, I had a question.
Sure.
On over the 16 on slide 5, I think. It was 16.3, number 1. I got confused on what you were saying about just the number 1.
On slide 5?
Yeah.
Okay. Number 1. Is it? Oh, let me share the screen. I'm looking at it and I'm like, do you see it? Let me share the screen. Okay, this slide number 5.
Yeah.
Number 5. And number 1, yours, which number 1, top one or bottom one?
Top one.
Okay, it's saying here, if the volume increases, the pressure decreases. And I was trying to use an example of your car tire. if you
Okay.
take a car tire and you measure the pressure, it should be somewhere around maybe 32 psi. Okay, so it has an X amount of matter in that tire. Now, if you take all that air out of your car tire, all that matter, and put it into a bigger tire, like an 18-wheeler tire, you see, do you anticipate that tire to be full?
No, we flat.
It'll be flat, and even that pressure probably reads 0 because the volume is much bigger, right? Much bigger
Okay.
volume, and so the pressure drops.
Okay.
Does that make sense?
Yeah, that makes sense.
Yeah, and so what that says down at the bottom, P and the relationship between volume and pressure, that is an indirect, meaning that if I increase one variable, the other one goes down. Okay, that's an indirect relationship. Where number 2 and 3, those guys are direct relationship, meaning if I increase one variable, the other one increases proportionally, you know, whatever amount. So, you know, like for your gas pedal in your car, if I push the pedal down, gas goes faster, right?
Uh-huh.
So that's a direct relationship. As I release the gas pedal, the speed goes down, I should say, right? So that's a direct relationship. Now,
Okay.
but indirect is when I'm trying to think of something other than the car tire, that when you increase one, it goes down, the other goes down.
Okay.
That is indirect.
No, that does help.
Okay.
Thank you.
Yeah.
And
No,
and then I have one more question.
sure.
For the practice one that's in there. Do you know, does that give us the answers? Like, are we able to attempt that more than once?
What it is a PDF file.
The practice?
Yeah, the practice final exam, that's just a
Okay.
PDF file. So that gives you a idea of the type of questions asked in the final.
Thank you.
Okay? Yeah, you know, the questions obviously won't be the same, but the type of question will be the same. You know, obviously we're not gonna ask, you know, instead of saying what's 1 + 1, we might ask what's 2 + 2. That kind of scenario. It's still a math question, for example, but we're not going to be asking the exact same question.
Thank you.
Okay, yeah, no problem. Any other questions? Yeah, I got a question. What happened in the chat? Okay, Sam, thank you. Thank you too. You do have a good weekend. Any other questions? All right, well, it's been fun. You guys take care, and you know, thank you very much. I appreciate it. Bye-bye. I'm going to shut it down so I can create the upload.